This is Open Physics Education Modules on Magnetic Resonance Imaging. Magnetic Resonance Imaging, or MRI, provides 3D tomographic imaging of patients. MRI is based on a physics phenomena, nuclear magnetic resonance, or NMR. To understand NMR, we have to talk about nucleus. Nucleus is at the center of an atom, and it is composed of protons and neutrons. Some nuclei, such as those of hydrogens, spin and have magnetic moment, which means they're like tiny magnets. We call them magnetic dipoles. Shown on this picture is a hydrogen nuclear. Of course, this one only have one proton in there. And we use this arrow, of course, this is not physically there, this arrow to indicate they're like a tiny magnet, which has north and south, just for illustration purpose. When these nuclei are subject to an external magnetic field, they will precess, like they're rotating around like that, just like a spinning gyroscope precess under gravity. The frequency of such precession, or turns per second, is omega. It's equal to the gyromagnetic ratio gamma multiplied by the strength of the field B. There are two types of precession situations. One is the dipole precess aligned with the external field, like the arrow will point up here. And the other one is the precession against the external field. So the arrow of dipole point down. The aligned precession has lower energy, and that's the preferred state of nuclear. A nucleus can flip from low energy state to high energy state of precession by absorbing energy from radio frequency radiation. Here in this picture we have example of a dipole is precessing aligned with the external field, but if we send in radio frequency wave, and if the energy is being absorbed by this dipole, and he will flip to a higher energy state, which is precessing against the external field. For this to happen, the frequency of the RF wave have to match the frequency of the precession. This is called the nuclear magnetic resonance. An excited nucleus precessing against external field can relax back to lower energy state by releasing RF radiation. Again, the frequency of released RF radiation equal to the frequency of the precession. This process is called the spin relaxation. Now we cover the physics basics. We can move on to MRI. The imaging subject of MRI are hydrogen nuclei. Why hydrogen? Well, human body is full of hydrogen nuclei. 70% of our body is water, H2O, and hydrogen is one of the fundamental elements of all organic compounds. And every hydrogen nuclei is just a proton, which spins and has magnetic moment. We have learned that the precession frequency of protons can be calculated using this formula. We have the gamma is 42.56 megahertz per Tesla, it's the gyromagnetic ratio of proton, and B is external magnetic field used in MRI, which range from 0.5 to 3 Tesla for typical clinical MRI scanner. Here's an example how we calculate resonant frequency of hydrogen nuclei inside the magnetic field. So if the magnetic field is 2.0 Tesla, what's the resonant frequency? Well, we apply the equation and we take 42.56 megahertz per Tesla, which is the gyromagnetic ratio, multiplied by the strength of the field of 2.0, we get 85.12 megahertz, and this is about the FM radio frequency. How to do MRI? First, we need to put the patient inside a big, strong magnet. And then, let's look inside the body, see what happens during the scan. Suppose we are interested in one section of a patient body, and here just show a patient body here. There's a lung here in the middle, maybe the heart, and this is just tissue around the lung, and maybe bones. And we virtually divide it into 3 slices, and this is middle slice, and this bottom slice. When there's no magnetic field, all protons or hydrogen nuclei are orientated randomly inside the body. Now we put the patient inside the magnetic field of an MRI scanner, and the field is pointed up on the Z direction. We can see protons are now precessing along the Z-axis, and most of them aligned with the field and sitting at the lower energy state. Please pay attention to these vectors here. We use the vector to indicate the direction of the magnetic field, but also the strength of the magnetic field, indicated by the length of the vectors. You can see that the magnetic field is not uniform along the Z direction. It's actually increasing along the Z direction. So we call this Z gradient field. As a result, the top slice of the patient is subject to the strongest magnetic field, so the protons in this slice precess the fattest. In the middle slice, the magnetic field is weaker than the top slice. As we know, the precessing frequency is proportional to the strength of magnetic field, B. So the middle slice protons will precess a little bit slower than the top slice protons. At the bottom slice, the protons subject to the weakest field, so its precessing frequency is the lowest. Now we send in excitation RF pulse. The frequency of the RF pulse is set to only matches the precession frequency of the proton in the middle slice. Only the protons in the middle slice will resonate with the RF radiation, absorb energy, and be excited to higher energy states. As you can see, this excitation is very selective, controlled by the frequency of the RF pulse. This step is called slice selection. Note that for the sake of easy illustration, all the protons shown in this picture are excited from low energy state to high energy state. The actual fraction of protons that ongoing surge change is actually very small, in the parts per million scale. However, due to the sheer number of protons in our body, a tiny fraction of protons that's ongoing surge process will still give out strong signal later when they relax from high energy state to low energy state. After the slide selection, we change the magnetic field in a way that the field actually now changes along the y direction. The strength of the field increases along the y direction and is uniform on the z direction. So we call this y gradient field. So with this new magnetic field settings, the proton at a different y location will precess at different frequency. This on far end here we have the strongest field, and so we have these protons precess the fastest, and then a little bit slower when we come in, and a little bit slower still, and slower, and even slower at this end. So you can see the precessing frequency changes along the y direction because the y gradient field. So these excited protons, or hydrogen nuclei, tend to relax to lower energy state and release energy by emitting radio frequency waves at the frequency equal to their precessing frequency. So the top row here has the highest frequency, so when they relax, they emit high frequency RF waves. And then the second row, frequency a little bit lower, third row even lower, and then fourth and fifth row have lower still frequency here. Another interesting thing to point out here is look at the amplitude of the radio frequency waves. They're actually proportional to how much proton are in that location. So the far end, we have lowest number of proton in those regions, so the amplitude is lowest. And in the middle row here has the most proton in those regions, so the emitted RF wave is the highest, largest amplitude. So we can use the frequency to tell us where these waves come from along the y direction, and also we can use the amplitude telling us how many protons are there in those locations, in that y location. So this we can encode basically the location and the number of protons into this radio frequency wave signal. To produce those excitation RF pulses, we need MRI coils. And there's an example of a head coil for head imaging. And we also need these coils to receive or listen to the RF radiation emitted from the protons or hydrogen nuclei during their relaxation. And those signals are then sent to the computer to be analyzed. So we can use the frequency information of the RF signal collected by the coil to find out where are the protons, as the frequency depends on the location. We can also use the amplitude of the signal to find out how many protons are there. This is called frequency encoding. This is one of the basic principles of MRI imaging. MRI can use search technology to generate a map of proton density inside the patient body. We can see that the RF signal from the protons actually decay over time. We call it T2 relaxation. And also, the time takes protons, which is hydrogen nuclei, to relax to low energy state. We call it T1 relaxation. This T1 and T2 depends on the local chemical and physical environment of the proton. So that makes them sensitive to the tissue type. So we can use the T1 and T2 relaxation time to help us identify different tissues in addition to the proton density. This table shows different tissues have different relaxation time T1 and T2. And some diseased tissue also show changes in the relaxation time. So this information will help us improve the diagnosis of disease. Here are examples of MRI brain image. On the left, you have the proton density image, and basically just showing how much hydrogen in different type of tissues. And on the right, you have the T1 weighted and T2 weighted image. You can see different type of tissues it's highlighted differently. So MRI is very good on soft tissue imaging. You can see here the brain tumor and the brain, and you have the fat layer under the skin here. And if a person has some joint pain, often an MRI is done to see the soft tissue, different type of soft tissue around the joint for better diagnosis. Sometimes MRI contrast agent is used through intravenous injection to image blood vessels. MRI contrast agent is magnetic. It changes the relaxation property of protons that in or near the blood vessel significantly and enhance the image contrast. These are MRI images of brain after stroke. On the left is the image without contrast agent. On the right is with contrast agent. You can see the bleeding inside the brain is much clearer with contrast agent. Okay, MRI safety. MRI requires super strong magnet. The magnet used by MRI scanner generates magnetic field as high as 3 Tesla, which is about 60,000 times of Earth's magnetic field. To produce such strong magnetic field, we need 100 to 200 amps of electric current to flow through the magnetic coil. That current is 10 to 20 times larger than the current flows through your hair dryer. To avoid extensive energy consumption under such high current, most MRI scanners now use superconducting coils. These coils are cooled down to 4 Kelvin or minus 269 Celsius degrees to achieve zero resistivity. Once established, the magnetic field costs almost no energy to maintain. With such strong magnetic field, people have to be very careful around an MRI scanner. No pacemakers or magnetic object is allowed in the room. In summary, MRI stands for magnetic resonance imaging. It utilizes the magnetic property of hydrogen nuclei, which is protons. Hydrogen nuclei persist under the strong magnetic field inside the MRI scanner. They absorb or emit RF waves at their processing frequency. The RF frequency indicates the location of the nuclei when a gradient magnetic field is applied. By exciting hydrogen nuclides and detecting the RF radiation emitted from them, MRI scanner can produce 3D images of patient. Safety rules must be followed around the MRI scanner due to the extremely strong magnetic field.